Right, for double layer ARC, also following the quarter wave optical thickness design, this is the design formula that we have, where N naught and N sub are basically the refractive index of the first medium and then the substrate, which in our case is silicon, and N1 and N2, the ratio of N1 and N2 basically represents the two refractive indexes of the two layers that we are going to select. So since same as before, we did some literature survey about double layer design, and we found out that magnesium fluoride zinc sulfide is one of the widely and commonly used materials for double layer design. Um, and similarly, silicon oxide and titanium oxide is also one of the commonly used design, which offers a reflectance of 7% between the ranges of 400 to 1000 nanometer. And similarly, this previous design gives us the reflectivity of 2.7% to 4.3%, which is much lower compared to the silicon titanium oxide design. So for our design, we selected magnesium fluoride, which has the refractive index of 1.3798 at the wavelength of 500 nanometer, which is our design wavelength. And once we have the refractive index of the first material, then we can find the refractive index of the second material by using the following relation. Because we already have the refractive index of the silicon, of the air, and our selected material magnesium fluoride. It turns out that the second material that we would require would have to have a refractive index of 2.7248. Right, so this is the ideal scenario basically, and in order to get a right, so for the second material, we have to basically find the material that has the refractive index closest to this particular ideal value that we have gotten. So silicon carbide, from what we found from the refractive index website, silicon carbide was the closest that we can find, which offers a refractive index of 2.6849 at the wavelength of 500 nanometer. So this is our ideal, and this is the real value that is offered to us in the real world by the material silicon carbide. Right, same as before, since we are using the double layer now, so this is the chain that we are essentially going to follow. We would first find the gamma C, followed by gamma B positive, followed by the impedance as seen by the second material B, followed by the negative reflectivity as seen by the second material, followed by the gamma A positive, which is the reflectivity as seen by the as seen on the right hand side of the first material, followed by the impedance of the first material as seen by the first material, and followed by the negative wave coefficient. Finally, the reflectivity as seen from the initial surface. Right. So discussing its results. So this particular chart right here shows us both the graph for double layer quarter wave optical thickness for ideal with the magnesium fluoride, and the real, which is silicon carbide with the magnesium fluoride. If we are looking at this chart, it doesn't look much different, but if we zoom in around the 500 nanometer wavelength, we can clearly see um, that the ideal design basically offers zero reflectivity at 500 nanometer wavelength, whereas the real design, which is with silicon carbide, basically does not offer 0% reflectivity at around 500 nanometer, but still they are very close. As you can see, the difference is less than 0.25, sorry, 0.025%, and it's almost negligible. So our design of double layer quarter wave optical thickness with magnesium fluoride and silicon carbide is very close to the ideal design, and it would work um, quite efficiently in real life as well. It should also be noted that the bandwidth that it offers is quite large, because if you see here, the bandwidth is quite small, and as you can see that the zero reflectivity is only around 500 nanometer, and for the bandwidth for the frequency before that, and for the wavelengths before that and the wavelengths after that, the reflectivity tends to increase much higher. Whereas if we look at the bandwidth in the double layer design, you can clearly see that the bandwidth is around 100 nanometer because for about 100 nanometer or so, the reflectivity is zero. So again, this is quite efficient compared to the single layer. Same as before, this is a MATLAB code, and then finally we for the non-quarter wave optical thickness design of normal incidence, we had to follow this methodology where we are going to treat these two segments as a signal segment, and then using the relation of of this particular relation right here, we can find the contour plots for the phi 1 and phi 2, and then we can look at the intersection of the real and imaginary part, and we can basically select any point on these contours in order to design the non-quarter wave optical thicknesses. So essentially phi 1 and phi 2 are going to give us the thicknesses of the sorry two layers that we select. And we selected one of the points. We simply took out phi 1 and phi 2 from that particular point, and then same as before, using the chain of uh, reflection coefficients and impedances from the transmission line theory, we obtain the following plot. And if we zoom in a bit, we can clearly see that for non-quarter wave optical thickness, it also goes to zero. Although this non-quarter wave optical thickness is not an ideal one, but a real one with magnesium fluoride and silicon carbide, only with the only difference of being non-quarter wave thickness. But you can clearly see that at 500 nanometer, the reflectivity goes to zero. Um, and this right here, so before that, I just shared the code with you. So same as before, this particular is the ideal quarter wave optical thickness design. This particular here is the um, silicon single layer ideal ERC quarter wave optical thickness design. This is the double layer with magnesium fluoride and silicon, and this is again the double layer quarter wave optical thickness, effective reflectivity. Then we have the ideal design. Then we have the ideal design effective reflectivity, and so on. These are the rest of the plots. So if I just run it quickly, you can see the obtained plots right here. Also, you can change. Sorry. So these are the plots that you already saw in the analysis that I showed you. So if you want to make any changes regarding the material of your choice, you can simply change the refractive index right here, and you can have the analysis done in requirement with your chosen design. And the rest of the code basically remains the same. So I will share this code in the description, and you can use it to design with your particular material for anti-reflection coating. Right. Quickly summarizing all that we've done. So we can clearly see that various design of ARCs that we have. The first one was the quarter wave optical thickness single layered with the tantalum pentoxide as well as an ideal, and both of them pretty much offers the same effective reflectivity, but you can clearly see for ideal design it's much lower. And then for the quarter wave optical thickness double layer silicon carbide and magnesium fluoride design, it's quite lower compared to the single layer, and similarly for ideal is even lower than the that is also lower basically than the single layer. And finally, the non-quarter wave optical thickness design, where we use the contour to find phi 1 and phi 2, offers much lesser reflectivity as well. So essentially, we can clearly see that the quarter wave optical thickness design is the most efficient one, because or the effective reflectivity it offers is the lowest right here. So essentially, it also varies for material to material and from refractive index to refractive index, as well as different various wavelengths. For our particular design wavelength and for our particular requirements for AM 1.5G spectrum, um, this quarter wave optical thickness double layer works the best. And again, like I will share the MATLAB code so you can have the design done by yourself. Right. So thank you for watching, and I'll see you in the next video.